Enlightened. Kevin is from AME, and he's talking about fractional derivatives and robot swarms.
You take derivatives every day. A while ago, you planned your journey to this room based on what you know about your walking speed, or, depending on the time of day, your running speed. Your speed is a derivative. It's the rate of change. It's the first derivative of your position with respect to time. The second is your acceleration, how your speed is changing. Acceleration changes too, and to measure that would give the third derivative. We can take derivatives as many times as we want. It's like a machine. X squared goes in, 2x comes out. 2x comes in, 2 comes out. And this is well known in calculus. We do it all the time. We apply it to all kinds of functions. But in my research, I stick the function in and I pull it out before it's ready. I take half a derivative, 1.8 derivatives, negative derivatives. Yeah, I went there. And these are all legitimate mathematical operators called fractional derivatives. Fractional derivatives are so little known and so underexplored in engineering that simply finding a new way to use them has turned into my PhD dissertation. What is this new application? Imagine you are in one of 1,000 self-driving cars traveling together on a freeway. You don't see that every day, yet. We want the cars to avoid crashing into one another, but we also want to make sure they maintain a certain speed. After all, you have places to be. So we set up controls between the cars that enforce the spacing and the speed we want, and now we've got a robot swarm. We can model the behavior of the swarm using regular derivatives. We can write differential equations for one car at a time, 1,000 times. Or we can capture the same behavior using fractional derivatives with a fractional order differential equation model that you could write on one line of a piece of paper. Fractional order has benefits in simulation and control, but my research shows that it can also be useful in monitoring. We can measure the order of a system from data, and if it's not what we expect, we know something has gone wrong with the system. In the example of the cars, maybe we're having issues with spacing, hopefully too much spacing, of course. But regardless, the fractional order model that we get from the data can give us information about the defect, both where it is and how bad it is, and therefore make it easier to get the system operational again. Because you all have places to be, and that's not changing. Thank you.